Welcome to this webinar presented by the IET's Anglian Coastal Local Network, which represents members in Norfolk and Suffolk. Welcome also to folks from other parts of the UK and indeed globally. I'm delighted to welcome you all, and I wish you all a happy new year. I'm Kevin Foster. I'm chairman of the Anglian Coastal IET Local Network, and I'll be your host for this evening. I'm delighted to welcome our speaker, Leonid Ponomarenko. Leonid graduated from the Moscow State University. In 2005, he completed his PhD at the University of Amsterdam, where he was studying two-dimensional electron gas in semiconducting heterostructures. After completing his PhD, he joined the group of Professor André Grimm at Manchester University, who a year earlier isolated graphene for the first time and won, jointly with Kostya Novoselov, the Nobel Prize in Physics in 2010. Leonid moved to Lancaster University in 2013 to start his own group researching his interest in two-dimensional materials. He has been a Royal Society University Research Fellow since 2013. So Leonid, over to you.
Good afternoon, everyone. So my name is Leonid Ponomarenko. I'm from Lancaster University. I'm really happy to present this talk here today. And to make this session more interactive, I would like to use this facility, which is called Mentimeter. So if you have your mobile telephones, please take a picture of QR code, and this will actually lead you to a website, which is this website, www.menti.com. So alternatively, if you don't have a mobile phone, you can take a QR code. So just go to this website. So this is menti.com. And once you see the page, please enter the code that you see on the screen. So 50603656. So this will allow me to not only talk to you, but also to ask you some questions. So hopefully this presentation will be not too boring, so you can actively engage in the talk itself. So once you reach the Menti website, so you will see my picture, and there was a title of this talk as well. So I will just try to share what you are supposed to see. So this is something that you will see. And just to, as a test question, I would like you to answer one simple question that will appear in the second on your mobile phone. And this question is about what is graphene. So it doesn't really matter what answer you will give, it just to test the facility. Also, there is only one correct answer from these three questions. Okay, now I can see that the people are trying to answer, and I'm really happy that quite a lot of people actually are able to reach Mentimeter. So what is graphene? Is it chemical element? Is it two-dimensional crystal, or is nanoparticle? And I'm glad that most of the people guess it, well, not guess, but probably knew it correctly. So indeed, graphene is a two-dimensional crystal. Okay. So with this, I will move to my second slide. So graphene is a two-dimensional crystal made of a carbon atom. It's not chemical elements. So it's made of carbon atoms and carbon atoms only. And we have, we know quite actually a few different forms of carbon. So carbon can exist in many different dimensional forms. So the most common ones are three-dimensional form of carbon, which have been known for hundreds, maybe even thousands of years. They are diamond and graphite. So diamond is a cubic form, graphite is a layered structure. So in 20th century, some other allotrope forms of carbon have been discovered. So one of them is a zero-dimensional form, so-called buckyballs of fullerenes, which were discovered in 1985. So of course, you may ask why this is zero-dimensional form if it has a finite size in all 3 dimensions. So the answer is that this zero-dimensionality is in terms of how electron moves in such structure, in such a molecule. So electron is not only a particle, it's also a wave, and zero-dimensionality means that this wave cannot really propagate through such structure. So a few years later, one-dimensional form of carbon has been discovered. These are so-called carbon nanotubes. And finally, in 2004, two-dimensional form of carbon have been isolated. This is what is the subject of today's lecture, today's presentation. And as you have heard, this was a subject of a Nobel Prize in Physics in 2010, only 6 years after the discovery. So how we can imagine graphene? So probably the simplest way to do it is to start with a crystal structure of graphite. So it's made of carbon atoms. These carbon atoms are strongly bonded with covalent bonds in plane. So they form so-called honeycomb lattice in planes. And different planes are weakly bound together with much weaker van der Waals forces. So these forces, interplane forces, are so weak that if we rub a graphite crystal against paper, then these bonds will break, leaving a small crystallites of graphite on the paper. That's basically how the pencil works. So what is graphene? So if we just take a monolayer of graphite, and that's it. This is graphene. So the first theory on graphene have been proposed, published in 1947 about electronic properties of graphene. It was not named graphene at the time. So the reason for that is that after Second World War, there was a huge interest in graphite because this is an important material for making nuclear weapons. So graphene is sort of natural first step for calculating properties of graphite. So we basically have to learn first, or model first graphene layer, and then add weak interaction between different layers. But for a very long time, it has been believed that such material couldn't exist until it was isolated in 2004 by two scientists, two researchers working in Manchester University. So Andrei Geim and his former PhD student, Konstantin Novoselov, they managed to isolate graphene, and not only isolate, but actually they made some groundbreaking experiments. So basically they made first field effect device out of graphene, and they managed to convince all scientific community that this is really a very interesting material. And when everyone get convinced, they got Nobel Prize pretty soon. So it's very unusual that a Nobel Prize is given only 6 years after initial discovery. And Kostya Novoselov, he was 37 at the moment when he got his Nobel Prize. So he is one of the youngest Nobel Prize winners ever. So why this material is so exciting? So here you can see some superlative properties of graphene. First of all, it's the thinnest material that you can think of, just 1 atom thick. So nothing can be thinner, definitely. But it has many other interesting properties. First of all, mechanical properties. So if we calculate the stiffness of this material, of course, per unit of thickness, not absolute stiffness, this would be the stiffest material known. It's stiffer than diamond. At the same time, this material can be stretched quite a bit before it breaks. So this is the most stretchable crystal. So up to 20%, we can stretch it up to 20% and it still doesn't break. So these two properties together make graphene the strongest material ever measured. So stiffness and the fact that we can stretch it quite a bit. But not only mechanical properties are very exciting. So it outperforms all known materials in terms of heat conductivity and current conductivity at room temperature. And if we get more technical and look at properties such like mobility or effective mass, then graphene is also a champion in many respects. So in terms of highest mobility, so the effective mass is essentially zero because of the very special band structure of this material. It also has the longest mean-free path. Graphene can be also considered as a membrane. Also, it's just one atom thick membrane, but it's still membrane. It's quite amazing that this membrane is practically impermeable. So even helium atoms cannot penetrate through graphene. So if we add to this quite impressive list of properties the fact that graphene is transparent and chemically inert, we of course can think of hundreds, thousands, maybe different applications of graphene. And that's why scientific community, not only scientific community, is so excited about it. So let's first consider how graphene can be obtained. So this is, so usually if I give this lecture in person, I take some pieces of Scotch tape with me and small graphite crystals and demonstrate it in person to the audience. But since I cannot do it now, I really have to show you how to do it on the screen. So if we have a small graphite slab or some flake of, so it looks like a flake graphite crystal, we can put it between two sticky layers of Scotch tape as shown on the image. So here we have a Scotch tape, and between sticky layers of Scotch tape, we have a graphite crystal in this red circle. So now if we pull the two ends of the Scotch tape, then this graphite crystal will split in two. This is again because the attracting force between layers is very, very small. So it's very easy to break. So now we can fold this Scotch tape again, but not exactly along the same line as it was folded initially, and pull ends again. And in this case, each crystal, so we had two of them, will split again in two. So now we have 4 different crystals, and we can repeat this process again and again, and every time a crystal will be thinner and thinner. Right, so at this point, I would like you to do some math work with me, and this will be your next task on a Mentimeter. So how many times we have to repeat a procedure which was described on the previous slides in order to get to a monolayer of graphite, which is graphene. So just to repeat, when we do the first cleavage, our initial crystal becomes 2 times thinner. When we do, when we fold and unfold Scotch tape, our crystal becomes 4 times thinner, and we can repeat this procedure as many times as we need. So the question is how many times we have to do that. So assuming that our initial flake was roughly 0.3 millimeter thick, so that's normal thickness of graphite flakes which are available, which actually researchers use for making graphene. So 0.3 millimeters means 3 × 10⁻⁴ meters. So it's hard to say what the thickness of a monolayer is, but as a good approximation, we can use the distance between layers of graphite, which is well known from the X-ray diffraction. So this separation between layers is approximately 3 angstrom. or if in SI units, this would be 3 × 10⁻⁻10. So we have to make our graphene crystal 1 million times thinner using Scotch tape. So now I will try
1632.
I will just try to switch to Mentimeter again. Okay, so now your questions should be visible on your screen, and you can either use a piece of paper to make these calculations. If you have time, I will just wait roughly maybe 1 minute, or if you are not ready, you can just guess, and then we will see the correct answer. So 1 minute roughly, so that everyone can get some opinion about it. Okay, so it's a good response rate. So we have so most of the attendants think that it's 20 times. Quite a large group of people think it's 10,000 times. So what is a correct answer then? Right, so in order to answer this question, we have to ask first how many times thinner the initial slab will get if we do it, if we repeat this procedure n times, and just continuing this logical steps that we have started with. So on step number n, the initial slab will become 2 to the power n times thinner. So in order to get correct answer, we just have to solve simple equation. 10 to the power n is equal to 1 million, or 10 to the power 6. And if you still remember how to use logarithms, then we just take logarithm at the base 10 of both parts of this equation, and the simple calculation with a calculator will tell us that it's 20. You can also get the same result if you remember that 2 to the power 10 is roughly 1000. So 10 to the power 20 should be 1000 times 1000, which is 1 million. So the correct answer is 20. So congratulations to all of you who actually give a correct answer, 20. Of course, if you are very, very lucky, you may get it quicker. So if you're extremely lucky, you just may pull one atomic layer from the surface of a graphite crystal. But 20 is the correct answer if you every time split a crystal in two. So the next we will go into the electronic properties of graphene. So graphene has very, very simple structure. So it's carbon atoms arranged in what is called honeycomb lattice, as shown on the right-hand side. And as I said already in 1947, the band structure of electrons in graphene has been calculated. So the band structure is, if you don't know what it is, it's how energy depends on the wavelengths or K vector of electrons. So electrons are propagating through the crystals as waves. So these waves can be described with wavelengths or the wave number. and dependence of energy on the wave number is really the starting point of any investigation of electronic properties of any material. So if we are interested only in electronic properties, not interested in optical properties, that all we need from this curve is really neighborhood of the very small energies. So we only have to consider how these curves look at the very small energy range. And there we will see that it looks like two cones touching each other. So for those who are familiar with band structure of semiconductors, you can recognize the valence band. So this is the energy range where at absolute zero temperature, all electronic states are occupied with electrons. And there is a conduction band. That's where all states are empty. However, it's different from conventional semiconductors in a sense that, first of all, these two bands are touching each other. So in conventional semiconductors, there is what is called band gap. So there is a finite energy separation, separating conduction and valence band. And second huge difference is that these bands usually are parabolic. So graphene was really the first material discovered where these bands were conical. So the dependence of energy as a k vector is a linear function, not a parabolic. So that's also was a well, big surprise when it was confirmed experimentally, because electrons in graphene, due to this kind of dispersion relation, basically mimic behavior of relativistic particles. So that's why quite often people call graphene a CERN on a tabletop. Okay, so what Geim and Novoselov did in 2004, that they not only isolated graphene, but they also placed the film of graphene on silicon wafer. So as schematically shown on the bottom right image. So here you see silicon, oxidized silicon wafer. So silicon is conducting material, silicon oxide is an insulator. So they prepared exfoliated graphene on top of it and added some gold contacts to it. And they were able to study the resistance or resistivity of graphene and study how this resistivity changes with applied voltage between graphene and silicon substrate. So this is basically gate voltage. So this is the simplest field effect device, and they have observed that resistance of graphene actually changes with gate voltage quite significantly. So exactly at zero gate voltage, resistance is largest. That's because our so valence band is fully occupied and the conduction band is empty. So that's normal. Normal semiconductors, they are insulating if they are not doped. However, if we apply either positive gate voltage, so we put more electrons, because it sort of work like a capacitor, so we put more electrons in graphene, we start to fill the conduction band with electrons, and these electrons help material to conduct. So the resistance, as you can see on this plot, is dropping. So the resistance as a function of gate voltage is decreasing with increased positive gate voltage. Similar behavior observed with negative gate voltage. The only difference is that now we are not adding electrons, we're actually taking electrons from the valence band. So we are leaving some empty spaces, and these empty spaces actually behave as electrons with a positive charge. So we call them holes. And it's quite common in semiconductors to have both either electronic conductance or hole conductance. So this is nothing unusual. So they have shown that something which is not initially a semiconductor, because graphite is metal, or to be precise, semi-metal, can actually show field effect. Because no one have seen a field effect in metals before. It's simply impossible because there are too many electrons in any metal we can't really change a lot density of electrons in metals. We can only do it in semiconductors. So it works as a field effect device. The question is, can it be used as a field effect transistor? Because not every field effect device can be considered as a good field effect transistor. So before answering this question, yes, I would like to also add that we can actually prove that we have different type of charge carriers, electrons and holes, by measuring what is called hole resistance. So normally we apply current along the hole bar and measure a voltage also along the hole bar. But if we measure voltage between two contacts which are on the opposite side of the hole bar, this is called hole resistance. This hole resistance tells us two things. So first of all, the sign of the hole resistance, positive or negative, will tell us if it's electrons or holes. And second, the value of the hole resistance will tell us how many electrons actually we have in our conducting materials, density of charge carriers. Right, and once we know the density of charge carriers and we know the resistivity, which can be converted to conductivity, we can calculate another important parameter for engineers especially, which is called mobility, which plays a very important role in making semiconductor devices, and especially how noisy they are and how fast they are. So it was realized already in 2004 that mobility of charge carriers in graphene is quite high. So 10,000 centimeter square per volt per second. This is standard unit how mobility is measured. Also, it's not as SI units. And a few years later, it has been shown that this mobility can be even increased to a value of 1 million. Also, for that, we have to go first to low temperatures, and then we have to make graphene suspended. So we have to remove silicon oxide because it's not a very good substrate for graphene. Okay, so now what really we want from material to be used as a field effect device. So if we are talking about digital applications, then field effect transistor is nothing else but an electronic switch. So the electrical current which flows between two electrodes, which are called source and drain, should be controlled by the voltage applied to the third electrode, which is called gate. So there are many, of course, different transistors on the market. They have all different parameters. But if we're talking about an ideal field effect transistor, then it should be a fast and non-leaking switch. So as fast as possible, essentially. So what does it mean? It means that if the gate voltage is in the range, which is called off state, then the current between source and drain should be essentially zero, should be negligible current. If voltage on the gate is corresponding to on state, then current between source and drain should be high. So the current between gate and either source and drain should be negligible all the time. So the gate shouldn't be leaking, essentially a capacitor. And last but not least, so the switching between on and off states should happen immediately, instantaneously. So once we just change the gate voltage, then the state of the channel between on and off should switch at the same time. Right. So here, keywords are that in off state, source drain current should be negligible. And second keyword is that the transistor should be really fast. Okay, so now let's, of course, nothing is ideal in this world. So the current in off state cannot be infinitely small. It can be zero. So then the important parameter that researchers and engineers use when they are making transistor and judge if transistor is good is so-called on-off ratio. So it's a ratio between currents in on and off states. And in order to be suitable for digital applications, this ratio should be at least 3 orders of magnitude, at least 1000. So now let's have a look again at the field effect in graphene, because I'm about to ask you a question. So what, in your opinion, is on-off ratio in the field effect device shown on the left? So in order to answer this question, you have to think which point on this plot corresponds to best off state, which point corresponds to best on state, and then calculate the ratio between current or conductance in on and off state. So I will just again switch to my Mentimeter. So I will go to next slide. And well, best of luck. Try to answer the question, please. So is the on-off ratio in this case just 1? Is it more like 10? Is it 100 or it's 1000? So once it's 1000, we can say, well, this is just good enough to use in digital applications. So I will wait 20, 30 seconds probably. Okay, I think that's probably enough time. So what I can see from a response that a significant fraction of listeners think that graphene field effect device is suitable for digital applications. Also, some significant part think that on-off ratio is about 10. So what is the correct answer then? Okay, let's have a look. So what is on and off state in this case? So the off state is the state with the highest resistance. That's where current is the lowest. And as you can see, the lowest current should be at 0 gate voltage. And it's about 6 kilo ohm. So the most conducting state is when we apply the highest voltage possible. So the highest voltage possible is 60 volt. Above, if we apply significantly more than that, we will just the electrical breakdown of the insulator will happen. And here resistance is, well, it's probably hard to say, but it's definitely probably half of the kilo ohm or so. So between 6.5 kilo ohm, the ratio is roughly 10. So all of those who give answer 10, they were correct. And unfortunately, all of those who think that graphene is already suitable for as a field effect device for digital applications, so they were wrong. So in graphene, in best graphene devices, on-off ratio at room temperature is only 20. So there is no proper off state in such device, and the reason for that is because graphene doesn't have a band gap. So the conductance band and valence band, they just touch each other. And if there is no band gap, well, material cannot be insulating. Okay. Right. However, it's not the end of the story, and don't get disappointed, because I will show you later that we can actually overcome this difficulty. So we can make graphene transistors with high on-off ratio, but transistors for digital applications, they are not only transistors that we are using in electronics. So we also need speed, not only the on-off ratio, but also speed. So there are a type of transistors which are called high mobility high electron mobility transistors. So these transistors, they have to be fast. So that we should be able to switch between on and off state as quick as possible. So that will allow us to work at high frequency. So the figure of merit for this kind of transistor is a cutoff frequency. And this frequency is inversely proportional to the time that is needed for electrons to travel between source and drain. So we can qualitatively understand this relationship in the following way. If we are in the off state, and then we switch our transistor to the on state, so the electrons start to flow, we cannot switch again into the off state before at least one transistor, at least one electron pass under the gate. So that basically sets the limit for the highest frequency, cutoff frequency. And as you can see from the simple image, this time which is needed for electron to travel under the gate is simply the width of the gate, L, so the distance between source and drain, divided by the drift velocity of electrons. And from this simple relation, you can actually understand what should be a strategy in order to make transistor fast. So we have to either make this distance smaller, or we can increase the drift velocity. So the first approach is to make transistors smaller, and that's basically what semiconductor industry was busy with for the last 60 or 70 years. But now we sort of reach saturation or limit where we can't make transistor much smaller. So then the second approach is, of course, to make electron move faster. And the drift velocity of electron is the product of the electric field, which is proportional to the voltage that we apply to our transistor times mobility. So again, we have this important parameter mobility for graphene, which allow us to make transistors faster. So we, of course, can increase electric field, but we cannot go also really, really far because, again, of the breakdown of the material. So once we reach the maximum value of electric field that we can apply, then we have to think about the best materials suitable for these transistors. So different materials have been used in semiconductors. So organic semiconductors are quite popular, but they usually have very low mobility. So no way of making very fast devices using organic conductors. So popular metals such as copper or gold, well, they cannot be used in field effect devices, but the mobility in these materials is of the order of 50. So in silicon, very popular material of choice at the moment in semiconductor industry is about 1,000 centimeters square per volt per second. So there are materials which are much faster than silicon. So these are semiconductors which is called 3-5 semiconductors. So they are not just materials, but they are actually heterostructures. So they have pretty complex structure in them, essentially just like any transistor. And the mobility in such structures is about 50,000. So now I will have a question for you, and this is not really a question, but more like a guesswork. So what do you think is mobility of graphene? Is it really good material for high electron mobility transistors or not? And with this, I will just switch to another slide on the Mentimeter. So what do you think is electron mobility of graphene? Is it 10, more like in organic semiconductors? Is it 1,000, like in silicon? Is it more like 100,000, like in gallium arsenide structures? Or it's so fast that it can be as large as 1 million at room temperature? Okay. Well, I have to say that we have a lot of optimists here today. That's good. But the truth is that the mobility is roughly 100,000, not 1 million. This is because at room temperature, electrons are really scattered on mainly on vibrations of crystal lattice. So the thermally excited vibrations of crystal lattice, and it's impossible in any semiconductor to make it at room temperature 1 million. We can do it at low temperatures, no problem. But at room temperature, we are limited by phonons. And I'll just go back to my material, my slide. So the room temperature mobility of graphene is 150,000. So it's kind of step forward compared to existing gallium arsenide structures, even the best of them. But it's not 1 million. So it sort of makes sense to try to use graphene for fast transistors, but of course it will not give us a gain like 1 order of magnitude compared to existing 3-5 structures. Okay, so on the previous slide, I have written that graphene, high quality graphene should be placed on boron nitride. So boron nitride is really ideal substrate, and this is the reason for that is that boron nitride is like a cousin to graphene. So it has all allotrope form similar to graphite. So it has a hexagonal form like white graphite, often called cubic form, which look like a diamond, and it's actually as hard, almost as hard as a diamond, but also fullerenes in nanotubes. And the reason for that is become obvious when we look at the periodic table. So boron and nitrogen, they are sitting on the both sides of carbon. So if for some reason nitrogen is giving 1 electron to boron, they become like 2 carbon atoms. So that's the reason why crystallographically or mechanically, these two materials are quite similar. However, they are very, very different in terms of electronic properties. And the reason for that is that graphene has inversion symmetry. So if we take a sheet of graphene and turn it 180 degrees, it will transform into itself. We cannot do that with boron nitride. And for that reason, graphene is a very good conductor, and boron nitride is one of the best insulators. So it has a huge gap between conductance and valence band of the order of 6 electron volts. This is really a lot. So boron nitride, therefore, is ideal substrate. So it's atomically flat. So the reason why graphene on silicon oxide is not so good is because silicon oxide is rough on a nanometer scale, but boron nitride is absolutely flat. So when we put a graphene on boron nitride, electrons can just travel many millions interatomic distances without being scattered. That actually makes them so mobile. So the mobility is that high. So boron nitride was first material which was studied after graphene, two-dimensional material, but today we know a few dozens of different materials which can be isolated in the form of atomic planes. So some examples are shown here. They are can be even derivatives of graphene, for example, like fluorinated graphene, which is two-dimensional analog of Teflon. But there are some other materials as well. Some examples. What is even more interesting, that we actually can combine these materials together. So we can place one material on top of each other, making like a 3-dimensional stacks of this material. So this is kind of artificial, new way of making artificial 3D materials with new properties. I would say engineered properties, and this has been done. What is even more interesting, that it's not only the order which makes a difference, which is important, but also the orientation. So if there is a rotational misalignment between two different layers, then the property of such stack again change. So this is very, very hot topic at the moment in graphene research and in research on two-dimensional materials. Right, so what about transistors? I told you that there is a way around, and indeed, we can make graphene field effect transistors with high on-off ratio. And I'm really glad that I have been a person who actually proposed this idea, and it turns out that it works. So what we have to do, instead of making a planar device, so not use graphene just as a conducting channel, we just make a vertical device. So we take 2 graphene layers. One of them is drain and source, and they are separated by the thin insulator, for example, boron nitride. So if this insulator is very, very thin, it works as what is called a tunneling barrier. So current can actually flow through it, but the current is quite small. What is interesting that if we place a gate electrode and apply electric field, this electric field actually penetrates one of the graphene because it's so thin and change the properties of this tunneling barrier. And current can change a lot. So that was tried first with boron nitride. We increased on-off ratio to 50, which was kind of better, but not so great. But then we started to use different materials like molybdenum diselenide or tungsten diselenide. So with molybdenum disulfate, as shown here, you see examples of VI curves. So current versus voltage between source and drain, what's called bias voltage, at different gate voltages. So if we look at the slopes of this curve around 0 voltage, it will simply give us the conductance, which we can recalculate into conductivity. So now if we plot this slope as a function of the gate voltage, we will have a curve which is shown on the right. And you can see this is a logarithmic scale. The conductance, conductivity changes a lot, and that means that on-off ratio is also very high. So if we look at this part as on state, and somewhere here, when conductivity is very low off state, then this ratio will be at least 6 orders of magnitude, more than enough for transistors to be used in digital applications. Okay, I think I'm running out of time a little bit. So this result, as you can see, so here there is a reference, 2012. So in 2012, we have on-off ratio as large as 6 orders of magnitude. You may ask, where are graphene-based integrated circuits? Where are the transistors now? Well, the answer is we cannot make integrated circuits yet because we don't have a method for fabricating graphene on high quality graphene with mobility required on wafers. So far, all these proof of principle devices have been obtained using the same Scotch tape that Andrei Gaiman and Konstantin Novoselov have been using in 2004. So there are some scalable methods available, but unfortunately, they are not as good in terms of mobility as mechanically exfoliated devices. So you may heard for example, in use that some companies are proposing graphene, producing graphene in tons, which is true, but the quality of this graphene is very, very poor. So for example, using a method which is called chemical reduction of graphene oxide, indeed we can produce tons of very tiny, small graphene flakes, which are just a few nanometers across. And this material can be used, for example, to make composite materials, to reinforce some plastic, something like that. But this is very, very far from applications in electronics. So more promising methods are, most promising one is called chemical vapor deposition. But the highest mobility achieved in this method, and this has been now for quite a few years, is only 3,000, which is not enough. And the graphene obtained on such wafers, they actually transferred on wafers from copper foil, is not a monocrystal graphene, but it's actually many, many polycrystals which are grown and overlapping on the so it's a polycrystal, so it's many, many crystals merged together. So absence of scalable production method is the biggest obstacle at the moment for using graphene in electronics application. So unfortunately, I'm running a little bit out of time, but I would like to also tell you some another approach for using graphene for field effect transistors, maybe in distant future, like, I don't know, 10 or 15 years. So this method has been around for quite a while, but for different materials, and it's called single electron transistor. So the idea is the following. So we make a device which has a source and drain. So these are two metal contacts, but they are separated. So they have a small metallic island in between, and they are separated from each other by tunneling contacts. So this is in real space, and on the top, this is the energy. On the energy potential. Okay, so if we apply the voltage between source and drain, we change the energies in these electrodes, and because we raise the potential of one of the contacts, then due to potential difference, electrons start to tunnel through the tunneling barriers and current flows. However, if dot is really, really small, then in order to transfer one electron to the dot, we have to charge it. But small dot means small capacitance. And in order to charge such a dot, we have to provide some energy for this electron. And this energy is E squared, which is charge of electron squared divided by capacitance of this island. So if capacitance is small, this energy is large. And if this energy is larger than EV that we are applying, then current cannot flow. This is called Coulomb blockade. So we can use this effect to make transistors. So if we make a gate to this dot, we can change electrostatic energy of the dot by applying gate voltage. And then once this level, which is appeared due to Coulomb blockade, once this level get in the energy window between source and drain, then current can start to flow again. So if we plot the conductance of such device as a function of applied gate voltage, we will see some peaks. So these peaks, it's exactly when this level is in the energy window between source and drain. And you can see here, there is an on state when device is conducting, and there is an off state in between these two peaks. So this device is called single electron transistor. And it was a really, really hot topic in 80s when these transistors were made of traditional semiconductors and metallic islands. They work only at low temperatures. So we actually have tried to do this with graphene, and we have actually succeeded. So indeed, we made the device of graphene. Instead of tunneling barriers, we just made a constriction. So that's old paper, 2008. But we indeed observed the Coulomb blockade, and we have shown that such device is working. Fortunately, it's working, as you can see, at temperature 300 millikelvin. So in order to make it work at room temperature, we have to decrease dot by about 100 times, which is not possible with current methods of lithography. However, in completely irreproducible way, we manage actually to etch this device, and actually we get small dots in these constrictions, and it turns out that this device is actually working at room temperature. So if you are interested in details, you can have a look at the paper. Right. So how basically what we learned from this is that if we look at the distant future, where all electronics is made of graphene, we can think of graphene field effect transistor, which look in the following. So we have a source on the left, drain on the right. In the middle, we have a quantum dot of graphene. So this is this small island. And then we have a side gate also made of graphene. So why this is interesting and important is because this is transistor which is made of carbon atoms, so graphene only and nothing else, no doping, no other materials. This is what's called top-down approach. So it's a more favorite approach for making devices. That's actually how we do make them. So bottom-up approach is interesting, but no one knows how to make large circuits out of it, molecular electronic. But what is really important here is that because bonds between carbon atom in graphene are so strong that this structure will be stable at room temperature, even if we apply some reasonable currents. So if we try to do similar structure out of anything else like metal, it will simply not work, because passing the current will sort of knock these atoms from their positions, and this device will stop working. Okay, so kind of I'm approaching the end of it. So is graphene a new silicon? So also it's promising, but the answer is no, not at least in the next 10 years. So what do we need to make graphene and new silicon? Well, we need a technology which will allow us to grow these sandwich structures on wafers. So, for example, if we figure out a method where we can grow 10 atomic layers of boron nitride, then it's followed by a bilayer graphene, not just simple bilayer graphene, but the twist angle between two layers of graphene 1.2 degrees, then it's followed by bilayer of tungsten diselenide and capped with monolayer graphene. When we learn like something like this, how to make it, how to grow it, it's kind of similar to what already is done with molecular beam epitaxy in semiconductors. But now we have to do the same with two-dimensional crystals. So then, of course, we can talk seriously about graphene being new silicon. Or we need a technology which will allow us to do lithography on graphene with atomic precision in order to make these quantum dots and single electron transistors. So at the moment, such technologies do not exist. So we have very nice material, but we don't know how to deal with that. Okay, so this actually brings me to probably one of my last slides, but this is not a slide, but a cartoon. So there is a big European program which is called Graphene Flagship, and they come up with this cartoon, which I would like you to watch. And this would be instead of conclusions for this talk. So it's about 3 minutes long.
The Simple Show explains graphene. This is graphene. Let's call him Mr. G. He is the first material that is two-dimensional. This gives him a unique set of properties. Since 1859, many scientists were looking for graphene using complex experiments. But the first crystals of graphene were discovered in 2004 using a very simple and effective method, namely ordinary Scotch tape. During Friday evening experiments in Manchester, scientists noticed small parts of graphene on the tape used to clean a graphite stone. The two scientists, Andrew Geim and Konstantin Novoselov, were awarded with the Nobel Prize in Physics 2010 for this simple but groundbreaking experiment. Thanks to the Scotch tape method, this area of science grew extremely quickly. And today, hundreds of laboratories all over the world deal with different aspects of G research. What makes Mr. G a really super material is the combination of his unique properties. G is the first 2D crystal ever known to us, the thinnest object ever obtained, and also the lightest one. G is the world's strongest material, harder than diamond, and about 300 times stronger than steel. G conducts electricity much better than copper. G is a transparent material. G is bendable and can take any form you want. And this unique super material gave birth to a new class of crystals that are also just 1 atom thin. And what's more fantastic is that these can be shuffled with each other to engineer new materials on demand to meet the special needs of different industries. All these factors move graphene swiftly from the G Research Laboratory to the G Marketplace, driven by demand from industries where such super materials are required: aerospace, automotive, electronics, energy storage, coatings and paints, communications, sensor, solar, oil, and etc. Thanks to mass production methods intensively being developed, expect to meet Mr. G in person soon. The Simple Show explains.
Okay, so that's it. Thank you very much. And I think we can now start with questions if you're not too tired.
Leonid, thank you so much for a very fascinating presentation. Absolutely captivating, and I think you've given us definitely a view of the future. I see there's at least 17 questions, so folks, if you've got a question, please put it in the Q&A tab. And I think we should move straight on to questions. And my colleague Ian Buxton will be handling the questions. So Ian, over to you.
Thanks, Kevin. So without further ado, I think we'll just get straight on, Leonard, if that's all right. Angus asked, why was it thought previously that a monolayer of graphite couldn't exist? Is there a simple answer to that?
Simple answer is, well, consider a cling tape. So it's once you do something wrong with that, it will just sort of collapse and turns into a ball, because graphene has very high surface energy. So it's essentially it's a surface. Surface doesn't like to be large. So unless you figure out how to stabilize it with the help of placing it straight away on some substrate, then it should not exist in a free form. There is also some theoretical consideration for that as well. So there is a theorem which is called Mermin-Wagner theorem, which basically tells that two-dimensional, infinitely large two-dimensional crystals cannot exist at any temperature above absolute zero. It tells us that if we have an infinitely large dimensional crystal, any thermal excitation will have very, very large amplitude and it will destroy it. Of course, graphene is not infinitely large, so they are small flakes. And also, they have a substrate. So that's why we can't really apply this theorem. I mean, theory is correct. It's just not very applicable because it's for the infinitely large objects. Okay, I hope it answers this.
Yeah, thanks, Leonard. So the next one is maybe a simple yes or no. Is it possible to make a 1 molecule thick edged blade? So I guess he's thinking of how sharp you can make things.
So probably it's possible. So, okay, so freestanding graphene exists. So I would say there are pictures in the internet you can look at, which look exactly almost like that. So it's look like a knife. The reason why it's stable and doesn't crumble like a cling tape, it will probably take a little bit too much time to explain, but the keyword is fluxural phonons. If you go to graphene and fluxural phonons and freestanding graphene, then probably you can find answer to your question. But the simple answer is yes, you can make kind of nano knife with a blade of 1 atom thick or thin.
Great, thanks. From Alex Wood, why were there Nobel Prizes for fullerene and graphene, but not nanotubes? Do you know the answer to that?
Well, I am not a member of Nobel Committee to answer this question, and I think they release their notes like 50 years after the award. So if we wait 50 years, we can check why it was not awarded. I think it was proposed many times, but the reason why nanotube didn't get it is probably because everyone was initially excited that graphene nanotubes is in fact ready field effect transistor. It actually works really, really well. But the problem is that it's only one transistor. So we need many, many nanotubes, millions of nanotubes arranged on a wafer to make an integrated circuit, and no one knows how to do that.
Okay.
So that's probably why it's not a subject of Nobel Prize.
Okay. Let's go on to the next question. Is there a machine that can synthesize graphene from graphite using the folding method?
Not that I'm aware of, no.
Okay, that's good.
And it will not get us too far because we cannot really cover the whole wafer of it. I mean, it should be really large monocrystal of graphite, defect-free. No, I don't think it will ever be made. It's not the way I think to proceed.
Fantastic. Peter Lord asks, can graphene decay or reform back to graphite over time?
No, graphene is stable. It may be less stable than graphite, but graphite is super stable. No, so yeah, it will just stay. I mean, at least hundreds of years, unless you do something nasty to it, warm it up to 600 Celsius or something. We'll do use some nasty chemicals. It's very stable.
Okay. Are the properties of graphene listed on one of your slides achieved at room temperature? So I guess that you did cover different properties at different temperatures, didn't you? So it may have been asked later, I guess.
Yeah, so the slide with superlative properties of graphene, the list which appeared at the beginning, it was all about room temperature properties.
Okay, that's good. Simpler one here, I think. Oh, they're just shooting in. Let's see where I'm going. Just a minute. Of the 10 superlatives that you mentioned, how many had been predicted prior to finding out?
That's a good question. To be honest, no, they were sort of kind of obvious because these mechanical properties, for example, mechanical strength was kind of relatively easy to predict, in my opinion, because covalent bonds between carbon atoms are very strong, and we know from, for example, from speed of sound measured in graphite that they are really strong. So mechanical strength probably was predictable. But yeah, it's kind of too complex question to answer.
Okay, let's. I think it's probably better on for the audience that we cover as many as we can rather than go into too much depth. So there was one that someone just asked, which was, what does EF stand for on the diagram with conic bands? So that was just a question of the mnemonic.
Go back. Are we talking about this one?
Well,
so can you repeat the question?
All he wanted to know was, what does E small f? So the it must have been on one of your slides.
Okay, so that's Fermi energy.
Fermi energy.
Fermi level of Fermi energy. This is the same thing as a chemical potential if we talk about zero temperatures, low temperatures.
Excellent. Ian Simpson asks, how large a sheet of graphene can be created? Is it only cleaved or can it be grown as a crystal like silicon? I think you talked to some extent at the end, you covered some of that, didn't you?
Yes. Yeah. So the high quality graphene with mobility, 150,000 room temperature, this exists only in the very tiny nanosheaths. So the largest size of this is maybe 50 micrometers. But using chemical vapor deposition, we can grow graphene film as large as 1 by 1 meter. They, however, are not monocrystals. So they have lots of defects. They don't have holes, but they have a lot of defects because that's many small single crystals kind of merged together. So there are this kind of defects of crystal lattice, but not holes. And it's monolayer of graphene, so it's not bilayer. Occasionally, it's always monolayer. It just mobility is not very high, but 1 by 1 meter, that's possible. Yes, with current technology.
Excellent. There's a question here I think is quite interesting, which is, does graphene interact with photons similar to silicon?
So graphene absorbs approximately 2% of visible light. So it does interact, so it's absorbed light in all visible spectrum because it doesn't have a band gap, but only 2%, which is a lot considering that it's only one atom thick. So for example, I'm just, you see me in front of camera, and between me and camera, there are many millions of layers of air, and light propagates straight away, and then just only one atomic layer absorbs 2%. So that's why when it become like 2 or 20 layers, graphite become opaque. But it's still 2% absorption of light. It means 98% transparent, which is very important for many kind of applications, because making conductors which are both, materials which are both conducting and transparent is important task for many applications like touch screens or LCD displays. So they all need it. And that's one of the, probably the first real industrial application of graphene will be exactly for that, to use it as a transparent conductive coating. And graphene is already good enough for that. It's just a little bit more expensive than indium tin oxide, which we're currently using in all these gadgets.
That answer is kind of related to one from John Nicholson, which I think was also covered in your little cartoon film at the end. He asks, where do you see future applications of this headed? Well, what I took from that film at the end was it's going to be in everything given another decade or so. But where do you see perhaps if I could just sort of focus it down, where do you see the first, perhaps, real application of graphene?
Right. So two most obvious applications, which I think almost there, are the one which I already mentioned. So transparent conductive coating, which is so the parameters of graphene which we can now grow are already good enough for that. It's just economically not very viable at the moment. But since indium tin oxide becoming more and more expensive now, and graphene is getting cheaper and cheaper, so at some point these prices will meet each other, and after that, most of the devices will switch to graphene. I can't predict when this will happen. Hopefully in the next 2-3 years. And the second likely application is sensors. So because graphene has such a developed surface, it's essentially a surface, no bulk, and it's conducting, and it can in principle interact with anything. It's completely separate topic for graphene sensor is a huge subject. I have no time to even touch it. But sensors, graphene sensors is next commercial application. I can't say which kind of sensors because range is also huge. It's
okay.
20 different areas.
The next question is from Richard. How are the graphene properties degraded if they are 2 or more layers thick? And how can you be sure the layer produces 1 layer thick? Thank you, he asks.
Okay, so indeed, bilayer graphene exists, and it's very, very different material from graphene. Just like graphene is very, very different from graphite. So the straight so there are non-contact methods which allow us easily to distinguish one from another. And this is what's called Raman spectroscopy. So I probably shouldn't go into detail, but it's kind of instrument which many laboratories have. So if you put the graphene on substrate under Raman spectrometer, shine light, measure spectrum. From the spectrum, you can immediately tell if it's a monolayer graphene or bilayer graphene, or distinguish 3 layers of something like that. But about stability, I'm not sure if I understand the question, but graphene is stable. So monolayer or bilayer, they will just stay at room temperature and ambient conditions. They will just stay like that forever. They will be covered, of course, immediately in nanolayer of all kind of water and everything that is flying in the air, but which will dope graphene. So if we measure resistance of graphene over time, the resistance will change, but it will change only due to doping, which we can, for example, by slightly warming it up or putting it in the vacuum, we can remove it. If we, for example, encapsulate graphene in boron nitride on both sides, then it will just stay in the same form essentially forever.
Excellent. There's a question here from David James, who I think is hoping to get his name onto the paper. He says, as a physics undergraduate at Lancaster University, I did a project in 68/69 using vapor deposition to grow single crystal graphite on a nickel substrate. Would this have been relevant to the
I think you are breaking up. Can you repeat
well,
last sentence?
So he said that he'd use vapor deposition to grow single crystal graphite on a nickel substrate in 68 and 69. Would this have been relevant to the development of graphene?
So that's exactly what CVD method is. So chemical vapor deposition, I guess. Indeed, it can be grown on a nickel, but copper in this respect is better material. So there are quite a few metals on which graphene can grow. The difference is that sometimes it doesn't grow like a monolayer, but a few layers graphite, or monolayer combined with bilayer with overlapping. So nickel, yeah, people use nickel to grow graphene, but tendency is, in particular, commercial companies which grow graphene, they use copper instead of nickel.
Okay.
So it's very, very relevant. It's very, very relevant. If this gentleman would continue to work on this subject, he could be the Nobel Prize winner.
I hope he's still listening. Is there any way to use high frequency sound to produce graphene? That seems a bit left field, that question, I have to say, but you may know more about it than I.
I'm not aware of such method. I presume the idea is to break bonds between layers using ultrasound. So there are methods which use ultrasound. So it's a liquid phase exfoliation. So, but it's not just sound, it's also a solvent. So you put crystal of graphite into a solvent, which kind of penetrates or almost penetrate between layer. But then if you sinicate it, it actually helps to solvent to go between layers and separate them apart. So I would say, yes, this is already used.
Okay,
graphene.
Thank you.
But not just sound alone.
Right. The next question is, again, slightly different in the sense it's raised by Ian Simpson. Does free graphene or nanotubes have similar health risks to asbestos? So a health and safety type question, I think. That may not be your field of expertise, of course.
So I think it's proven that nanotubes, they have health risk because they are like what's called filament. I don't know. They like a fiber similar to asbestos. So graphene in this respect is safer. I think like 10 years ago there was some kind of research on mice, but the results were kind of not confirmed. So the initial report was kind of bad, that graphene is can actually cause a cancer if it get into the lungs. But first of all, it's not that easy to get into the lungs. And then I think it has not been verified to confirm that it makes some, there is a serious health risk.
Okay.
Honestly, I'm not expert in this. None of my colleagues have died, but we are all only working with very, very small amount of graphene.
I think that's good enough. That's good enough answer for me. I think we probably just now to limit to a couple of last questions. Rich M asks, with such high current density, could this be the basis for high performing electromagnets?
Probably I don't. Okay, the simple answer, I don't know. I have some colleagues working in high magnetic field labs in, for example, laboratories, well-known laboratories, high field magnetic laboratories in Grenoble or in Nijmegen. They also working on graphene, but not. I haven't heard anything about using graphene as a cables or in cables for strong magnets.
Okay, that's good. And maybe we'll make this the last one before handing back to Kevin. It's one which has been asked by John Skelt. do you think we will ever see graphene used to support the cleanup of nuclear waste?
I don't know, honestly. I don't know
Well,
how this can be used. Probably not directly, but I have no idea. I never heard about even applications proposed for this.
Well, that's an honest answer.
Maybe
Leonard.
I'm not familiar with the corresponding literature as well.
Yeah, no,
So I cannot answer to this question, I'm afraid.
I think probably that's a good place to actually stop, and let's hand back to Kevin. Kevin.
Okay, so I will stop sharing the presentation.
Thank you, and thank you very much, Leonid, for a very clear and fascinating presentation. You've obviously put a lot of work into making the slides and the animation very clear, and I was really delighted to see a lot of very positive comments that have come in through the chat window. So I think you've delighted the audience with the information that you've presented. So big thank you on behalf of the IET and the audience on this webinar. Very, very much appreciated. I'd just like to thank Ian for grouping the questions, and for the audience, the participation. You've really engaged the audience, as I said before, lots of very, very good feedback. So thank you so much. I'd just like to remind everyone that we are recording the webinar. It'll take a little while for us to process that recording, but we will put it up on our community's website. So if you think you'd like to go over some of the material, then it will be available in the next couple of weeks or so. So I'd like to draw your attention to our next series of webinars. We've got an ongoing program in 2022, which is expanding rapidly. I'm delighted to say our next three webinars are organized already. We've got the next one on the 22nd of February. That's entitled The Strange Neighborhood of Black Holes by Dr. Ed Friedman. The one after that is on the 8th of March on railway communication by Dr. Felix Ngobia from University of Suffolk. And on the 29th of March, we've got machine learning making smartphones smarter from Somdip Day, University of Essex. Now we intend to roll out more as 2022 goes on, but these are the next three. If you're interested in those webinars, then the first two are, you're able to register for the first two. The third one we're just putting up fairly soon, so it's not quite ready for registration, but it will be fairly soon. So if you're interested in those webinars, then the link is shown on the bottom of the slide. Please click on that link and go through. So finally, it falls to me to thank the audience for your participation, and to thank Leonid for putting the webinar together, and also the team from the IET and the local network and IET HQ for putting the webinar together. So very much appreciated. Thank you for your participation. That concludes the webinar. You may disconnect now. Thank you.